8.8 complex number system. So in the beginning of this chapter, we said that square root of a negative number is not a real number. Now we're going to introduce a complex number system to include all of those kinds of number, all of those numbers. Right? So complex number used in a lot of applications. I stated, I give you example right there. So what we are interested in for this course is just to be able to do the fundamental operations of a complex number, meaning how do we add, subtract, multiply, divide. So first, we're going to have to look at the definitions. Imaginary unit. That will be square root of -1. We denote it with I. So it has a property of I squared is equal to -1. And with this imaginary unit, then we can talk about a complex number. A complex number has a real part and an imaginary part. And then we will write it in a standard form of A plus BI, where A and B's are real number. Every complex number has its conjugate, complex conjugate, which is the opposite operation of it. So for this sections, main thing that you need to remember is for any complex number, always rewrite it with imaginary notation first before you do any operation. So we're going to practice rewriting in terms of imaginary units. For the first problem, I'm going to write it down step by step, and then we're going to do it in a shortcut. So square root of -81. So this can be looked at as square root of -1 times 81. So using the properties, this will be square root of -1 times square root of 81. So I can look at this as I times 9, which is 9i. So starting from now on, we don't want to write it down every little detail like this first example. So when we see square root of a negative number, we know right away it will be a complex imaginary unit involved. So let's take a look at on the second example how I will write it down. So square root of -81. So right away I know that this will be square root of 9 times 2, and I will write it I outside of it, taking care of the square root of -1 mentally. Now I can simplify like regular radical numbers. Square root of 9 is 3, so my answer will be 3 radical 2i, which is another way of saying is 3 times square root of 2 times I. Okay, so this is how you have to see it. For example C, since I cannot simplify 5, so the only way that I can rewrite is square root of 5i using imaginary notation. And that would be my final answer. Now we want to look at adding, subtracting complex number. Adding, subtracting complex number, basically similar to idea of combining like terms. What we're going to do is we're going to add the real parts of a complex number with real parts of another complex number, an imaginary part of a complex number with imaginary parts of another complex number. So sort of like a combining like terms idea. So let's take a look at on the first example. So in this case, first we're going to have to rewrite it into imaginary notation first, because the second complex number, I can see that it will be 4 minus square root of -4 is basically 2i. Now what we can do is we can drop out the parentheses and then combining like terms idea. So real parts combined with real parts, which will become 6. Imaginary part combining together, 7i minus 2i will give me plus 5i. and this will be my final answer. And you want to write down your complex number in the standard form, which is a real part first and then imaginary part. Next example. So now I'm going to distribute it negative when we dropped out the parentheses. So it'll be 4 plus 3i minus 2 plus 6i, distributing the negatives. Then combining real parts together, which will be 2, plus combining imaginary part together, that will become 9i. And this will be my final answer. So adding, subtracting complex number. Next, multiplying complex number. So for the first example, notice that the first factor is involve imaginary unit. The second factor also involve imaginary unit. So therefore, we're gonna rewrite it with imaginary notation first. So this will become 7i times with 2i. Now, multiplying these two complex number, which will become 14i to the second power. According to the property, I to the second power is equal to negative 1, so it'll be 14 times negative 1. So my final answer is negative 14. Next, we're going to distribute this imaginary part of a complex number to another complex number. So this will become 4 times 5 is 20i minus 4 times 3 is 12i to the second power. Again, simplifying this, 20i minus 12 times negative I squared is equal to negative 1. So therefore, my final answer is 20i plus 12. Remember, you need to write down your answer in standard form, so there will be real part first plus imaginary part. So that will be your final answer. Next problem. Using the FOIL method to multiply the complex number. So first, we're going to rewrite into imaginary notations. So that will be 5 minus 3i times with negative 1 minus 2i. Foiling this, 5 times negative 1 is negative 5. 5 times negative 2i will give me minus 10i. Negative 3i times negative 1 will give me plus 3i. And then lastly will be plus 6i squared. Continue simplifying this, which I can combine the imaginary terms together. So that will be negative 7i plus 6 times I squared is negative 1. So therefore, this will give me negative 5 minus 7i minus 6, which is negative 11 minus 7i. That will be my final answer. Next example, we're going to use the shortcut formula. You have to remember that first minus last square, that is first square minus 2 times first time last plus last square. So first square minus 2 times first time last plus last square. That is negative 2, 5i, and then 5i. So negative 2 squared is 4. So that will become plus 4 times 5 is 20i plus 5i squared will become 25i squared. Simplifying a little bit further, I squared is equal to negative 1, so that will become plus 25 times negative 1. So therefore, this gives me 4 plus 20i minus 25. So my final answer is negative 21 plus 20i in standard form. Next example is multiplying the complex conjugate. You can see the negative 5 plus 4i, negative 5 minus 4i. So it's the operations is opposite. So this is a sort of like in difference of two square format. So when you multiply it according to the formula, this should be first square minus last square. So my first is negative 5, my last is 4i, which will give me 25 minus 16i squared. So 16 I squared is negative 1, so 16 times negative 1, that will give me 25 plus 16, which is equal to 41. And what we notice from here is if you multiply a complex number and its complex conjugate, your result will be a real number. And this idea, we're going to use it on divisions of complex number. Dividing complex number. So from the previous example in the multiplications, we saw that a complex number time and a complex conjugate will help me to get a real number. So similar idea from the radical, dividing by another complex number is much more difficult than dividing by an integers. So we're going to rewrite the denominator to become an integers. So the step that we take is multiply the numerator and denominator by the complex conjugate of the denominator. And then we're going to write our result in standard form after we simplify it. So by saying that 2 plus 5i over 5 minus 2i. So the complex conjugate of this denominator will be 5 plus 2i. So I multiply the numerator also by 5 plus 2i to get equivalence fractions. Multiplying this, the denominator we use difference of 2 squared. The numerator we can do the foiling. So when I FOIL it, 2 times 5 is 10. Plus 2 times 2i will give me 4i. And 5 times 5 is 25i. And then lastly will be plus 5i times 2i, that give me 10i squared. And the denominator will be 5 in first square minus last square. So this gives me 10 plus 29i plus 10i squared, so 10 times negative 1. 5 squared is 25 minus 2i quantity squared will give me 4i squared. So this allows me to get 10 plus 29i minus 10 over 25 minus 4 times negative 1. So numerator, when I simplify it, 10 minus 10 will become 0, so it will be 29i over 25 plus 4 will give me 29. So therefore, my final answer after I simplify everything, it will be just I itself. Let's move on to the next example. Multiply by the conjugate factor. So the conjugate, complex conjugate of this denominator will become -1 minus 2i. Always the opposite operation. So -1 minus 2i, I multiply the top as well. In the numerator, we distribute it. In the numerator, we distribute it. So -2 times -1 will be +2. -2 times -2i will become +4i. In the denominator, it's difference of two square formula. So first -1 square. My last is 2i quantity square. This gives me 2 plus 4i, 1 minus 4i square, which is 2 plus 4i over 1 minus 4 times -1. That is 2 plus 4i over 5. Because 1 plus 4 will become 5. So now we need to write it into standard form. So I need to split these fractions into this way. 2 over 5 plus 4 over 5i. So notice that we write down a real part and imaginary part separately. Last example. So for this one, 2i, you can take a look at this as a complex number. My real part is 0 plus 2i. So the complex conjugate for this will become 0 minus 2i. Or you can just say that -2i. So simplifying this, 3 plus 3i over 2i. So multiplying by the complex conjugate, which is going to become -2i, -2i. There are more than one way to do in this kind of situation when you only have an imaginary part of a complex number in the denominator. I'm trying to show you a very traditional way, right? Thinking about always like multiplying by the complex conjugate. So this will become -6i minus 6i squared over -4i squared, which is equal to -6i minus 6 times -1 over -4 times -1, which is -6i plus 6 all over 4. Now we write it into standard form, which is 6 over 4 minus 6 over 4i. You split the fractions and then rearranged it. So final answer will become 3 over 2 minus 3 over 2i. That's my final answer. The power of I. So let's try to pay attention on the first few power, right? I to the first power is I to the second power, from the definitions we know, property we know that is -1. I to the third power, I can rewrite it as I squared times with I. So that will become, well, I squared is -1. So therefore my final answer is -I. I to the fourth power, I can basically write it as I squared times I squared, which is -1 times -1 equal to 1. But if you look at I to the fifth power, I to the sixth power, I to the 7, and I to the 8, it repeats the first 4. So therefore, what you need to do is you need to only remember the first 4. And I'm going to show you an easy way to do it. So the strategy is this. If you have I to the very large number power, we don't have time to break it down like this and then continue, counting. So the way that we're going to look at is the exponent of I, if you divide it by 4, and if your remainder is 1, then the simplified value will be equal to I to the first power. If your remainder is 2, the simplified value will be equal to I squared. And then if the remainder is 3, it will be equal to the value of I to the third power. And if the remainder is 0, it will be equal to the value of I to the fourth. So let's take a look at on the first example. So here's the shortcut way first, and I'm going to show it you a more proper way to write it down. Okay, why we divide by 4. So according to the strategy, the exponent of I is 75. I divide it by 4. So 4 goes into 1 times 4, 335. So 4 goes into 8 times 32. So the remainder is 3. If the remainder is 3, this I to the 75 power is the same thing as the value of I to the third power. So my answer will be negative I, because I to the third power is equal to negative I. So basically how I got this answer so quickly, okay, using this strategy is this. Writing down step by step, I basically break it down I to the 75 into I to the fourth power. Let's put it this way so that you can see better. I to the 72 power times I to the third power. And I to the 72 power is basically I to the fourth power times with 18. So what happened is I to the fourth power is equal to 1, and 1 to the 18 power is still 1. So my only answer left over is what is I to the third power equal to. So 1 times negative I, which is going to be negative I. So that's how I got my answer so quickly without writing any of these steps. So now you can see why we are dividing by 4, because we want to group how many I to the 4 power do we have from this 775. Because that will always give me 1, and then it's easier to do the computation. So now that you understand both ways, let's stick with the shortcut. So I to the 92. So what we're going to do is we're going to divide the exponent of I by 4. So this is basically 4 goes into 2 times. That will be 12. 4 goes into 3 times. And the remainder is 0. And if the remainder is 0, the value of I to the 92 power is the same thing as I to the fourth. So we know that I to the fourth power is equal to 1, so therefore this is my final answer. And this concludes the sections.